Welcome, Arun. Welcome. Yesterday we did the first session. Welcome, Soumya. Good seeing you too. Please don't miss, everybody please don't miss classes. If you miss it, go back and review. But the problem with review is that sometimes it takes time to post it. I'll try to do it. Sometimes I'm not very that satisfied with the delivery sometimes, so I kind of I feel I have to add or edit and add something else and so on. But anyway, I'm going to post yesterday's stuff, but also I'm going to post today's stuff. Okay, by the end of today, I have already converted that into MP4, Supriya, yesterday's stuff. So I should be able to give you that link. I'll post it in YouTube, give you the link right away after the class within half an hour. But this one, it takes time, 2 hours, to convert approximately, the whole GoToMeeting format into MP4 file, so 2 to 3 hours it can take. All right. So welcome everybody. Arun, how HR you? You mean how are you? Mean is that what you meant, Arun? It says how HR you. Hello HR you. Hello everyone, maybe. Everyone. Okay. All right. Yesterday I did each 3 topics. Decision tree. Okay. I taught random forest. I also taught boosting, Adaboosting. Adaboosting is same as adaptive boosting. Actually, yesterday and if today you attend together, I hope you will get the essence of it, the deep value, the deep purpose, the deep smartness in which the boosting is working to help us predict better. Okay, so I'm going to review again that stuff today. Okay, and also go through with example data, and for Adaboosting, and also be a comparison between. I will also do multinomial versus how do we do multinomial models. You know what I'm saying? Multinomial means multiple classes. Because decision tree is usually yes or no type, and in the case of restaurant problem, it is just a binary case, right? Yes or no, whether somebody will wait or not. But we will see maybe sometimes 3 classes, 4 classes, 10 classes, 100 classes, who knows, right? But in those cases, what do we do? That's another thing I want to cover today. That's a dominant portion of this material is really reviewing it. So I hope you are kind of binding to that concepts, getting attached to it and then thinking about it, questioning it, challenging it, okay, challenging me, whatever, okay. But in the end, with today's, yesterday plus today, you should be really good about decision tree, random forest, and boosting, okay. And we will also include what is called most like, I'm not sure whether it will happen today, but the another type of boosting called XG boosting, that is extreme boosting. Okay, we'll cover that also. Maybe most likely not, but I may introduce that today. With that, boosting will be over, random forest will be over, decision tree will be over. Then we'll talk about next week and a new topic. Okay, how does that sound? That's my plan. Okay, in the process I will show examples, case studies also, because remember, you do want to show case studies, bring up examples of case studies so that you feel comfortable. How does that sound, everybody? Gautam, Rajesh, Ram, Avinish, and Arun, Gauri Shankar, Jeffrey, and so on. Okay, all right. Yesterday I actually got worried. Maybe I'm not getting across. I'm not teaching you to get you bound to these ideas. How many of you felt yesterday was difficult? You should be bold with me. I remember I told you many times, I'm just your friend. Is it a deal? I'm just your friend. Okay. So you should tell me. If you don't understand, you have to tell me. If you say, you have to tell me. Okay? Tell me. Everybody is good? Arun is saying this way. What does that mean? Is it yes this way or this way? Tell me.
He was asking a review as to whether it was fast or whatever he has changed is okay. He's going to take an example. Today's plan is okay with you guys or not? Let him know.
Yes.
With a cheerful sound.
Okay. Go ahead. Arun, you are trying to speak something or you said something, but I can't hear you. Sorry about that. Anybody else in the meantime while he is fixing on his side? Jeffrey, how do you feel? Do you find it? These formulas are very ugly looking, right? There is a logarithm, 1 minus epsilon divided by epsilon. Where in the world these guys get this kind of formula? It looks like bugs moving around, right? Epsilon looks like a bug, isn't it? With the 3 legs. Okay. That may be an issue, but the point is overall structure. Do you understand? But anyway, I'm going to repeat it. Okay, I'm not talking about it. I felt I should repeat it, so I'm going to repeat it. Okay, so welcome again. Now let's go over this this presentation deck. Okay. So we took this data set, which is whether somebody will wait at the restaurant. If they see that there are different scenarios. It is full of pattern, some pattern. There is a nearby. There is a bar inside the restaurant. There is an alternative restaurant nearby. It's a Friday. Is it raining or not? Is there must be a reservation or not? And is the person hungry or not? And what is the price? And what is the estimated waiting time as well as what type of food it is? Okay. So and we used information gain as a way of solving this problem. Okay, information gain is commonly used for decision tree. Okay, and it is also called sometimes a C5 algorithm. Okay, please note it down. C5 algorithm is also used as the information gain, okay, entropy concept. Okay, so so the information gain is this measure. Please remember that 1 minus entropy of x at any particular place. Okay, at any particular split. Okay, information gain is 1 minus entropy. So somebody might ask, what is information gain, right? 1 minus entropy of the split. Okay, which is also called uncertainty reduction. Okay, information gain is same as uncertainty reduction. Okay, so that formula is this for two variable cases minus of, it's a very funny function, right? For the first time you probably see, a function starts with a minus, right? But that's because, these are all, negative values. It's negative value because P and Q are between 0 and 1, right? Logarithm of value P, when it is between 0 and 1, it is a negative value. So it kind of makes it as a positive number. All right, so we found this, and also what is it for this is for 2 class, okay, 2 class information gain. This is entropy, and this is information, this is entropy, and this is information gain for 2 class. Even it's K class. In other words, there are K classes to be split, explored. Then this is the formula. Are you with me, everybody? So I'm just giving you some key ideas right now in the review, plus again kind of detailed review. So in this one, what we are saying is, the entropy, this is the entropy function, which is basically a number of bits needed for coding the message. The message is whether it is somebody will wait or not, right? That's the message. So the number of bits is maximum when there is so much uncertainty is there, and maximum uncertainty is when it is 0.5, right? When it is less than 0.5, the closer and closer and closer you go towards 0, you need less and less number of bits needed to code that message. Is that message clear to you in summary? Okay, so you just understand NSR, what is this bits and all coming? Why do we say bits is the number of bits is a measure of uncertainty at all? It is because you can see that when it is 0 or 1, definitely clearly defined cases, somebody makes a decision, you don't need any bits. It's already there. The information is fully resolved. When the information is not resolved, that's where you want to code that information into some measurement process, and that measurement process is entropy. Is everybody's good? Arun? Good? Okay. Jeffrey? Because it might be an interview question, what is entropy? What is information? It's possible. It's nothing wrong with it. If you say machine learning potentially, I doubt they will ask the question because there are some questions are more important than some questions, other questions. I doubt it, but if they come there, you can explain well. And in fact, even if they don't ask that, if you end up answering some other question, you can bring that definition to clarify yourself, okay? When they see that, no, you are able to explain clearly, they love you. Because clarity, people love clarity always, right? Confusion is very, very scary. Okay, confusion is scary. Yes. All right. So here is the example, and I took two situations to compare how to calculate the information gain. Is there everybody clear on that one? You just apply the formula 1 minus. The 1 minus because it is a starting point. In the starting point, 50-50, right? 50% of the people are making a decision to stay, 50% of people are running away. So what is the information you have to code there? You need 1 bit. If it is because it's 0.5, isn't it? So you need 1 bit. So 1 minus. Everybody's good? Okay, 1 minus the formula. Correct, Gauri Shankar? Okay. All right. Now that I calculate that, and then I find the first one, patterns, whether somebody's patterns are inside the room or not, in the restaurant or not, that gives you information gain of 0.541. But the type of food is information gain is 0 because this is 1 minus, this turns out to be 1, it is 0. There is nothing there because it's exactly same information on both cases. Do you understand what I'm saying? Do you understand, everybody? Why this turns out to be 0 and this turns out to be 0.541. So there is it's a maximum compared to this one. So that's your first splitting point. Is everybody good? That is your first splitting point. Okay, everybody's good. Okay, cool. But you can see that in the splitting point also the none case, actually it is it is a for sure situation, right? In the none case it is for sure situation. Why? Because you can see that in the none case 2 of them are left. It's a for sure situation. So your information gain is 0, right? So you don't have to actually you don't have to redo this part. In the same way you don't have to redo this part, but there is confusion here. So we are trying to resolve this one. What will help to resolve that, right? That is the next split. So among the 6 sample only this time, we find what is the next one. It turns out the next one is, you can check all the possible cases, different variable, but next one is weight estimate between 10 to 30, 30 to 60, greater than 60 type, right? That variable turns out to be the maximum information gain. So that's how you kind of split out every time. Everybody good? Everybody's good? Excellent. Now I do that continuously, and so you might wonder how did I know weight estimate, right? Because I check for every variable. We have to do it, computationally. We have to calculate it and do it for every variable. But so when it comes to the computational work in the computer, you don't have to worry about it. The algorithm is implemented there; it just quickly does everything. Okay, but this is just you have to go through every one of the variables. Whether it's a weight estimate or is a Friday or not, whether it is a pricey or not, whether it is a reservation or not, whether it is bar is in the place or not. All those variables, every variable you have to go through. It's not easy. It's very grudge work, but you don't have to worry about it when it comes to the computer-based application, right? Because it's already packaged for you. Everybody's good? Okay. All right. So that's how we solve this problem. And then comes, and also I want to give you this reference for you for an interesting example for understanding calculation at second step. Okay, at 2 steps. That I calculated that for you only for the first step, isn't it? So you can check this one. It's available, and I think this document is going to be given. It's already given to you link, or it's going to be given to you. Either one. Okay, don't worry about it. So you can, the drudge work, okay, grudge work or drudge work, whatever, people go through that. The second step, how do we do it, is explained there. So no worries. Now, so a decision tree can be built for this, especially for this case, a decision tree is built. Everybody is good on that one, right? A decision tree is built. But the thing is, people figured out that it is better not to just build one super decision tree, but many decision trees, and then combine them. That logically makes sense, isn't it? Does it make sense to you?
Yes, sir.
It should make sense to you. Maybe you are not able to explain to you, but it should make sense to you. The reason is, once a decision tree is built, it is not taking care of the small variations at different levels. Okay, because it just so happened the variations in the decision tree, one decision decision tree, one decision, right? Single decision tree. You kind of, once you enter, that's fixed. That level is fixed. You're not going to change. Again, when you enter the second one, it's fixed. It's not going to change. That's what one single decision tree is. But what might happen is that by potentially changing it may sound like it is less there at the second level, but in the it might turn out to be a better performer at the third level if you switch it. Potentially, it can happen. Okay, with a different variable, not the same set of variables. Small variations can add to the benefits. So what they found out is, okay, let's build a many trees. But then the question is, how do we combine many trees? The way to combine is, you check the output of one, two, let's say 10 trees are built. Okay? You check the output of tree 1, tree 2, tree 3, tree 4, tree 10. And among 10 trees, 8 times it is classifying to weight, and 2 times it's not classifying to weight. So it is still it's not 100% true. All the trees are saying weight. It may happen, okay? But if that is the case, then you use what is called majority voting. In this case, 8 times they said they are going to weight, 2 times they say that they are not. The algorithm says is not to weight. So majority is weight. So for that particular sample, the outcome is predicted to be weight. Does that make sense? Okay, majority voting. All right. So it turns out, in this example, there's a comparison here, random forest. So when you have multiple trees, it becomes a forest, and that is what is called a random forest. Okay, it's just a name, random forest. So the comparison is between random forest versus single decision tree, and we want to compare mean square error in prediction. That's what this means? Random forest, mean square error. Comparison with random single decision tree, mean square error. So the lowest mean square error is better, isn't it? Right? In prediction, yes. The lower the better. So your blue is always uniformly. That's the beauty of it. In other words, for whatever the 10 decision data sets they try to use it, in all the cases, it has lower mean square error in prediction. So it is uniformly better. That means you use it, right? Something is uniformly better. That means for all kinds of variations, it's always coming out to be, at least this 10 data sets, I'm saying. If it comes out to be less than the other one, it is better to use random forest than single decision tree. Everybody's good? Yes. Then I took the, yes, the question, please. You just said yes. Is that what it is? I thought I heard somebody sound, okay. All right, so I took next a data set, and actually I wanted to show you what's going on, right? And so the library random forest and library mass has the Boston data set, which is about median house value in thousands of dollars, and there are 13 variables available whether distance to the employment center is too far or closer, how far, right? Crime per capita. Accessibility to radial highways. That means radial highways means something, it's a circular road, right? So you go there, you come back, eventually you can come back to the same place. And then whether the person land is zoned for lots, that means residential, right? And then in the industry, non-retail business, non-retail business, tax, property tax, whether that house is on the Charles River or not. This is in Boston area, okay? So Boston has Charles River. And then people teach a ratio, nitrogen oxide, percentage black people above age 63. Okay, number of rooms. I think it's age 63, isn't it? Number percent minus 63. Yeah. No, this seems to be percentage, right? So it should be maybe a national average or the entire Boston. Boston is 63. Then they are saying in Boston compared to overall Boston, whether it's below or above. Below or above. Average number of rooms, L stat means, percent lower status population age, percent built before 1999. 1940. So in a neighborhood, what percentage is built before 1940? That's what age means. So with all these variables, very easy. You define the dependent variables in the 14th. This is, even though I put it in this way, this is the last variable in the data set. So I showed you that one last time. I can just quickly get you there right away. And I want you to get comfortable. Randomforest is very easy to do. That's why I'm saying, I said yesterday also, it is not easy to learn machine learning, but you have to go to the next step of how to conceptualize models. People who do Coursera, all those stuff, Udemy, they don't know how to conceptualize models. They'll just do what I'm doing right now. So you have to get there somewhere. That's where your capstone is going to help. You are doing a capstone also. Okay, capstone is going to help, and you should always talk among yourself as friends, or talk to us, talk to Supriya, talk to me, talk to the dean's office, and so on. Okay, given a collection, and look, this is what my manager is saying. This is the data I have. What am I supposed to do? Sometimes you may ask a question, but if you keep asking the same question again and again, and if you go through 100 cases, you are going to be good. Am I making sense? But it's only a matter of doing more work. What's the only way to gain knowledge? Do more work. You're doing practice, practice, practice. Are you with me, everybody?
Yes, sir. Yes, sir.
Are you committed?
Yes, sir.
Arun, Soumya, Gautam,
Yes,
Ram, Avnish, and Jeffrey,
Yes, sir.
Rajesh. Very, very
Yes,
important.
sir.
Why am I asking you like this, everybody? I want you to feel it. I want you to be there with me. Don't forget. Oh, Gauri Shankar, Uttamma. Gauri Shankar, are you with me, sir?
Yes, sir. Yes, sir.
Everybody, you do more work, you will be better. You will be better. Believe me, you will be highly respected. And there is no better thing for us when you get respected in your office, or when you go for the interview, you get a better job. Only way to win in life is practice, practice, practice. Of course, you might say, sir, there are a lot of things I have to do, and which one is I'm going to practice now? No, you have to select only few things in life. Don't do too many things like me. I end up doing it. But you know what? If you end up like me, then you'll become a teacher. Maybe you want that, I don't know. But the point is, don't try to concentrate on too many things. Be one thing best. And you're going to be the one thing is data science. Is that correct?
Yes, yes, sir.
Okay, thank you. Thank you very much. Gauri Shankar, I'm not seeing you. I don't have to see you all the time, but you can say yes, I hear that. That's good enough.
Yes, sir.
Okay, good. Very good. So let's just go back and see the quickly, Boston data. And for that, I have to call in the library, mass and library, two things, right? Two libraries, right? Forest and mass. Okay. So library. Can I do two packages in one sentence? Everybody? Random forest like this, can I do it? So, yeah, it's okay, right? Random forest. It did random forest, it didn't do mass. It doesn't say mass, it didn't say anything. So I'm going to call again mass. It didn't point to it. Whoa, could not find library work. Could not find,
It should be within the course, right?
No, it's not. Oh, yeah, I got it. Okay. This time it didn't complain. All right. It didn't say anything last time, and so this time it's okay. Now, with this, I can call in the Boston data because Boston data is available in mass. So that's what it is. Okay. So this is the 14th variable. The median household price is 14th variable. So we kind of do this. I'm not going to rerun it, but I'm going to show it to you. Okay, everybody, look at it. So these are the commands you have to use. Library random forest, library mass, data Boston, Y is Boston, comma 14, X is all the variables 1 to 13, and then I just put this one to get some help. Okay, so that's all to it. But then in the next page, I have the remaining commands. RF is random forest X comma Y. Very simple, right? So doing a model is many times is very simple because the computer does the work for you. But going beyond just getting a model is what matters. On both sides, what do we mean by that? after you get the output, in this case RF, you got to figure out what it contains and how to interpret each of them, right? That's one. The other one is, before you do random forest, you got to figure out, is that random forest right thing for you, okay, or something else. That is the before part. So in between is what usually people teach you, in all kinds of programs. Most of the programs teach you that, but you have to get there on the both sides of the world. That is, after you get the output, how do we use it, apply it, and in the other part is before you go for this command, what is that what is that you need for your work? Is the random forest, boosting, decision tree? From now on, we are not going to talk about decision tree except to learn more things, because we know random forest is better. We know boosting is better. Why bother, right? Nowadays, nobody does decision tree, one single decision tree. Okay? All your machine learning, AI, always use random forest or boosting. Okay. Now, I showed that the output here. Let's just do this one for one reason, because it has a lot of other things also I want to show it to you. Yesterday I didn't show it to you. Random forest x comma y, right? Is it y comma x or x comma y? One moment, please. X comma is over x comma y. So what happens is, maybe, I didn't define x. That was the reason. Okay, that's fine. Boston 14, that is the 14th variable for column. X is equal to Boston 1 2 comma 1 to 13. Okay, everybody good?
Yes.
Now I call random forest, and it is working, and I'm going to see what are the objects inside random forest. The output object. Output object is RF, but what are the elements? What are the members of that basket, right? Oh, these are the things, different things going on there. You have to know how to interpret each one of these things. Is everybody good what I'm saying? For example, so similar to R square, there is an R square also here, and then some of them no worries, but you eventually should know how to interpret it. This is the call. That means what is the model really? That's what call refers to. Okay, so it's going to come back with this one, right? Coefficients, forest, importance variable. Yesterday we saw that importance variable. One second. Okay. All right. And what is the y variable? What is the x variable is not mentioned here. In bag, local importance, MSE, mean square error, M try. That means number of variable you try, okay, for every split. So let's just find out. So how do I find out? RF dollar, because the members of an object is accessed using dollar symbol. We want M try. It is using 4 variables at a time out of 14. Do you understand what I'm saying? Every tree is built using 4 variables. And how do we select 4 variables? Randomly selected. It's okay. That's what they do in random forest. So, and then let's see one more thing. And so you can explore this thing. You should explore, okay? This is what it means, your commitment to the science. That means even if I don't tell you, you should go explore, get bogged down and then come back, oh, I don't know what is this, I want to understand this. That's okay, because there's only so much time we have between you and me. I can teach you, say enough of it, you should go and explore and come back. Okay? Everybody? Manish? Avinish?
Yep.
Okay. Entry. Let's see what is entries. That is number of trees. Okay, how many trees it built? The default is 500, but you can have more also. See 500. So if you want to change it, what you do is simply do entry is equal to here is 1000. How about that, right? You can do 1000. M try is number of variables, only 3 variables. How about that? It's doing that, right? Now, RF, dollar, R square. I'm just curious to know what is this R square is, okay? Okay. That is regression sum of squares, right? Something like that, right? Regression sum of squares. It's a percentage prediction. So as the number of trees increases, you can see that it is stabilizing to the higher prediction. It won't not necessarily it will increase systematically, but it will go into the higher and higher prediction. Okay, but after a while it doesn't improve a lot, so that's why typically when I build random forest, I got usually 2,000, 3,000 trees I built. Okay? And you can play with that, whether it is m try is equal to 2 variables, m try with 3 or 4 or 5, you can do any number of them, right? So that's what this means. Now, let me go back to, and then I showed you that percent variance exponent is 87.84. For the default values, right? M try is equal to 4, number of trees is equal to 500. And mean squared error. Okay, let's go back and redo this one. M try is equal to 4 and 500. That's the default. And now RF head, let's say tail. I don't, because tail is better than head, because as we go down, the R square is going to increase better, right? As we go down, that means that we do more work. RF dollar RSQ. Okay. So you can see that it just a little bit improved. And I asked this question yesterday also. 8.894 actually. Yeah, it is the same, isn't it? 0.8. No, it is a little bit improved. Are you with me, folks? See this one, 8.8784, but it is this one is currently it is 8794. So there is a little bit of because every time you do, a new random collection of samples are selected. Okay, remember that, huh? Are you with me, guys?
Yes, yes, sir.
Okay, thank you. So, well, okay, let's see the other objects inside. Oh, it also provides you predicted values. Okay, remember, I just built. I didn't do the test versus train. You should really do test versus train. Everybody is good on what I said just now. Right now, yes. I just built the model. I didn't do training and testing, split the data and then do the training and then go and, use the model object to predict it and then compare it with the actual in the test data set. You should do that actually. Everybody's good?
Yes.
Okay, remember that. I mean, I may not say this all the time, but when you do real life work, that's what you should do. You can't just build a model and go away saying that, oh, this is 87%. Can't say it. Everybody's good on that one. Right? Exactly. Very, very important. Okay. All right. So predicted is available as it is for this data. The new data it may be something else. For the given data, it will give you this. Okay. Out of bag times, number of times, out of bags done. So let's see. M try, M3, MSC. Let's see, MSC dollar. Not head, not tail. RF dollar. MSC. So this is the mean square error in the prediction. It should decrease, right? That's what it means. But decrease means it may not decrease systematically. See, it's for 10.17, it's 10.18 here. There is also 10.19 in between. Okay, but overall it should decrease. Because if you go to the head RF dollar MSC, you see it is much higher, isn't it? As we build more and more trees, it is your MSC is decreasing. That's what the idea of using random forest and more number of trees to form the random forest. Is everybody good on that statement? Correct?
Yes.
So, oh, you said yes. Okay. And then, so you should always, one thing you should do is anything you build in a package, you should check, hey, it's an object. I want to know what are the things it contains. LSC, use the command LS. Everybody's good? Remember this, no? Correct that?
Okay.
Okay, Avanish? Go.
Yes, sir.
Go.
Yes, sir.
Okay, thank you. All right, so let's see what else. So it is already predicting me for me, so I can do that. For the given data, it will predict, but that is not usually what is most important, right? You want to predict and check. When you're developing a solution, you have to check with a test data set. So that means, you have to use this command. That's what this command is. Predict RF, predict, or, you have to give this command with the new data is equal to, okay? predict RF comma new data is equal to test comma test $y. Everybody understands what I'm saying? Because you're going to compare the predict. This is the predicted value, right? This is the predicted value of the test data set. If I put new data is equal to test, is the new data set using this object, and I am predicting what variable? The variable because it is this data set is already given. It is defined. You don't have to actually put it. Test $y. Okay, are you with me, guys? You don't have to put it. You can put as well y. Y is there in the test data set. Good. So that predicts. Oh, this one is Let me tell you this. This is the. Let me tell you very carefully. I think probably I confused you here. This is predicting y value in the test data set. This is actual. Okay. So when you put the test $y is the actual y. This is test $y hat. And when we plot this, we expect it should lie on a line like this, right? It should lie on a line like this. The perfect model means a perfect arrangement. Not so good model means that it is spread out around that line. Okay, excellent. All right, so we did that yesterday, and then I also wanted to show you, because sometimes, oftentimes, not just sometimes, you want to check, which variables are actually explaining better the random forest, which variables explain the model better. So usually you can use the percentage increase in MSE, which essentially means that variable will decrease maximum percent MSE, mean square error in prediction, right? I don't like the word inc, but really it is about this variable is, well, maybe because, it is giving here, it is a percentage. You can put it in or decrease, it doesn't matter. But as long as you understand that this will reduce a lot of error in prediction. And next, this will reduce like that. Okay? Everybody's good? And there is also two measures besides this one. There is also the measure called purity. But purity is related to your entropy. Okay? Purity is related to your entropy. But you can use this one. MSE is fine. Easier to understand because we all know what is mean square error is, right? Everybody knows mean square error? Anybody who doesn't know mean square error? Everybody knows. Correcting Gaur Shankar. Varun?
Yes, sir.
Excellent. All right. Next, I thought I kind of went through boosting. Boosting reduces the bias of the weak learner and improves the variance reduction. Okay. Now, the prediction error improves the prediction error because it is concentrating on, at every stage, it is concentrating on misclassified observations in the previous step to do better job in the following step, so that whatever got misclassified in the previous step is better classified, correctly classified in the next step. That is the goal of the boosting method. That's what boosting means.
Sir, I'm not clear on the previous graph, sir.
This one?
Yes, sir. There are two graphs. I'm not clear on interpretation.
No, what I was suggesting is don't look at two graphs, only one graph you work on it. That is the MSE alone.
Mean square error.
Oh, you mean here? Here.
Variant da.
Okay. Well, actually, I don't have it here too. There used to, if you plot, if you plot, it will come two. But I picked up only one for a reason, because you don't need. You all know how to calculate, how to understand, how to interpret mean square error. So otherwise, I will define purity. It doesn't matter. You just use this one. Okay? Are you with me?
Okay.
All right. In actual calculation, when you do this var imp, right, in this command, it will get two outputs. But I picked up only this, because I know it doesn't matter. Okay. This is another benefit of coming to us. Remember, folks. Okay. The idea of you coming to us is to remove to remove unnecessary variations in knowledge search. Am I making sense? Unnecessary variations in knowledge search. Oh, could this be better, or could this, I'll tell you, don't go there, don't go here, do this, do this, do this. That's our job, because that is what is going to reduce your pain in searching for knowledge, in searching for doing the best practices. Are you with me?
Yes, yes, sir.
And I often say that also, no, don't do this, don't do this. For example, I think somewhere I made the point, there are 150 machine learning algorithms. When I was much younger, I go crazy, right? I do this, I do this, I do this, and then compare all that. It's useless. Because inexperience, this is where the teacher comes into play, right? Teacher tells you what is being practical. Okay? So inexperienced people found out there are only 5 algorithms that matters. Absolutely, and we are going to cover all of them. All the 5. One is logistic regression. Age-old logistic regression. Still is kicking and breathing, and it is fighting for its position. And it's doing well. You can be assured that many times our logistic regression will be beating even randomforest. Okay, got it. Second one is randomforest. Okay, randomforest does good job in many situations. Even though there are occasions logistic regression. Okay. Third, SVM, support vector machine. It's a great application. It does beat other things. Boosting. Fourth is boosting. Okay, fourth is boosting. It beats randomforest many times. Finally, average neural network. Neural network, average neural network, ABNNET. ABNNET is the package available. Okay. So these are 5. If you do your work with these 5, you are fine. You will succeed in your job. And that kind of statement only can come from a practitioner. That's why you are coming, and we provide this kind of intelligence to you also. Okay? It's a short path for success. If there are somebody beats it with one person and so on, it's not going to change life. You should be confident enough. Are you with me? Nothing is going to change because somebody works 3 days on it, but by the time your manager will say, look, I asked you to give me the answer today, you come back after 3 days, and then you are saying you got better algorithm. Nobody will buy that. Do you understand what I'm saying? Your manager will not buy it. Wait one. Chalta hai. I know what is that in Hindi? How do you say it, Avnish? Go home.
Ghar ja.
Huh? Jao. But go home, right? Home means? Okay. So that's what we don't want that, right? So these are practical issues, practicing issues. Okay. So okay, I give a long answer, Gautam. Rajesh, sorry, Rajesh. Your last answer. I hope it is you get it. Okay. Now let me go back to the this boosting. Okay, so one thing I want to introduce is the word weak learner versus strong learner. Please write it down. Weak learner, weak, W-E-A-K, not W-E-E-K, W-E-E-K, not W-E-A-K. Weak versus strong, right? Weak learner versus strong learner. Strong learner is one single decision tree. That's what is called a strong learner. We talk about it, learning, right? Machine learning. So it's all learner, learning. Strong learner means one single decision, super decision tree. Weak learner means little trees. That's what we are doing to combine them into forest, right? That's the terminology I want to get you for you to get used to. So we did that, and then I wanted to learn this package called Carrot package. There are more additional examples there. Please take a look at that one. Okay. It also talks about Adaboost, example. Here is the Adaboost example data. Okay. The same thing that I did yesterday, right? Is that everybody good what I'm talking? Is everybody good what I'm talking? Same thing, but it is done in R actually, just to just to show you what these things mean. Okay, we did that using hand calculation, and finally we combine three. They are calling it a hypothesis, which is same as decision trees. One variable decision tree for this example, right? Left or right, left or right, left or right. These are also called stumps. Decision tree that has only one variable splitting as left or right, left or right. It's called stumps. Please write down what is meant by stumps. Because stumps is very powerful. Just as left or right, left or right. Am I making sense? Are you with me, Arun?
Yes, sir.
Yes?
Yes.
Okay, I take the message, yes, and that's Priya. Is everybody else with me? Show that. Thank you. Show that. All right. So stumps are very powerful. It looks like only one variable randomly selected, and then we are checking left or right. Only one variable randomly selected, checking left or right. That's called stump. Instead of taking 4 variables, that's what happened in the case of the Boston house price, right? Stumps are very powerful. Why? Because it turns out to be a very practically powerful example. Maybe you have to do a lot more trees, but it is very powerful. So this is another example. It is part of my notes. It is there. It's embedded here. Building predictive models in R using the carrot package. In that there are examples here. This is a PDF. This is HTML. Very powerful. Max Kuhn wrote this. He is the one who points out 150 packages. Okay. All right. Next, I went into boosting, and then in the boosting, I kind of explained to you that this is what it is. So anyway, I will go and open the actual file. So let me open that file. Adaboost calculations. So here is the sample. But let me explain the data because it's very important to understand the data. So I have to open this one. This is the original publication embedded into the document. See, if you say all these things, it will become probably, nearly 250, 300 pages, okay? Even though it says only 85 slides, okay? These are all, each one is a document, a lot of details are here. Once again, I opened it, but what happened? I'm going to open from the, from the folder, okay? YAML folder I have. It is there. Boosting approach to machine learning, boosting an unusual and yet attractive optimizer. I'm looking for the original publication. It's probably there. GBM, iris data, case study, back propagation. So I think this is the one. Let me check. Is that the one? Okay, I'm going to check this. Yeah, the original guys. These are the original guys who developed the work. Okay. So I wanted to show you that example with the 10 sample points. They're talking about all of them. Basically a different one. So not this one. I don't want this. Okay, it's too much. Let me go and open that Acrobat. Not this one. Let me open this one or save this actually and then open it. Save. Not picture, okay. Review of, actually, okay, let me go over here, somewhere here it's there. No, it's neural network. So there is also reference for you. What is entropy and information gain? Okay, you can go through that in Stack Overflow. From Stack Overflow, I kind of referenced it here. So, okay, I want to go back to this.
So could you go to that mean square error 3?
I'm sorry, what is that?
Mean square error.
Which, what is the size slide number?
16.
Oh, 16, okay. Again, variable importance.
No, not this one. Mean square error 3.
Oh, mean square error definition. Is that what you want?
Yeah. Could you please explain why are we looking into mean square error? Why is it important in classification?
Okay.
They are
This is,
actually giving
remember,
practical.
yeah, 1 second. Are you going to explain, Supriya, or you want me to?
I think I've not explained to them.
Okay.
Still they are having doubts. So.
Okay, all right. Remember, mean square error is average of sum of squares or differences between actual versus predicted in median value, household value, right? House value. But you remember, this is not a classification. That's another important variation I want, information I want to tell you. This is actually, MEDV is what? MEDV is median home value, right? Which is a number, not a class. Is everybody good on that? Yes? So how come I'm using, I started decision tree, I went into random forest, but I'm using random forest for continuous variable. Random forest can be used for continuous variable also, not just for classification. Because in the decision tree also, the average value is below, the value of the house is below average, above average, or below some cut points versus above some cut points. It becomes a class, but it's actually using the value of the house. Do you get it, what I'm talking? So random forest can be used for both classification and regression. When the outcome variable is a continuous variable, it is called regression. Everybody's good? Please note down what I said just now. This is a question, can be an interview question. Okay, so random forest is so powerful. You can use it for classification, you can use it for regression. The package is built in such a way that it will resolve itself. Isn't it beautiful? Life is easy, right? Okay. But coming back to the performance of the algorithm, this is what you want, every time it predicts some value and you have an actual value for every time. And then you take the differences, that is an error in prediction. And you find the average of sum of squares of differences. That is called mean square error prediction. Is everybody's good?
Yes,
Mean square error. So you should have explained that. That's an interview question too, right? Okay. Thank you, Supriya. So I want to go to quickly. There was a presentation deck. I'm going to open it. Okay, give me a moment, please. It's a presentation deck, a small presentation deck, perhaps. Oh yeah, Adaboost, Gather Melly. I took this guy's presentation deck. I modified it to our purposes, to my liking, and these are the keywords I want to bring it up to you. Single decision tree, you already know it. Traditionally, one single decision tree was built and claimed that the problem was solved. Okay. Researchers realized that there could be multiple trees built and results combined for better prediction. Results could be combined for better prediction, right? Driven by the adaptive boosting method, which uses stumps as a tree. A situation of given support of a function, the output is derived using either to the left of the observed value or to the right of the observed value. That is what the stumps is about, and that is what is used in adaptive boosting. Is everybody good on that?
Yes, sir. Yes, sir.
And it can do even if the data are like this. What like this? Like this means there is all the plus cases are inside a circle type region. I kind of put the circle to show you, to get your attention. It's a circle type. Even if I don't have circle, if the points are plotted like this, okay. I want to get this guy. It's not. I'm not. Okay, there you go. See, even though I put like this, I kind of putting a line to the left and right, to the left and right, to the left and right, to the left and right. Everybody gets it? This is an Adaboost approach, isn't it? And it can even get circular region separation, right? Everybody gets. I'm sorry, there are a lot of birds coming up outside. Hundreds of birds. I got distracted. So everybody's good. What I'm saying? So it can even figure out solving a problem with a circular region. Everybody's good? And that's what I showed you by putting the circle there. So why? I'm hearing some noise behind, so please control it. So do you see what I'm talking? Everybody? Everybody raise your arm. It's very important. Yeah, thank you. Huh? Somebody, I'm going to mute, okay? I don't know who the. 1 second, please. 1 second. Arun Gauri Shankar. Okay, institute is quiet. Okay, I'll take out the revenue. You can say if you want to say yes, this. If you want to say question like this. Okay, that's easy. Thank you. And then I will unmute. All right. Now, do you get what I'm saying? When I saw this, I got really excited when the first time when I saw this one, this graph, what I'm talking, isn't it? For the first time, of course, later on you will see SVM can also do this. SVM can also do this. But a linear, logistic regression cannot do this. Am I making sense? Unless you build a logistic regression with so many stumps. You take each one of them as a stump, code it into a variable, and then build the model. Then it will be like that. Am I making sense? But Adaboost is very straightforward, very simple, very very beautiful. I mean, I was just blown away when I saw that. Oh my goodness, it can build us. It can separate a circular region, which is very highly nonlinear. Right? Everybody's good?
Yes, sir.
Okay, cool. So, but in order to explain that, I kind of took this samples. There are 5 of them pluses, 5 of them are negatives and minuses, and the data points are this is 2 and 3, this is 1 and 5. 1 and 5 results in plus, 2 and 3 results in plus, 3 and 2 results in minus, 3 and 2. That's what this means. Okay, x-axis is x1 is this, x2 is this. Let's call that way. Everybody, you understand how I am interpreting this? The reality is this pluses and minuses have to be separated out by this kind of, what we call this is a piecewise linear. Do you agree what I'm talking? Piecewise linear. Separator. We'll call it that way. Piecewise linear. That means you take the linear pieces, combine them, and then it separates the pluses versus minus. Everybody's good?
Yes, sir.
And it can get quite complicated. In fact, this is the infinitely piecewise linear. Infinitely. This is the infinitely piecewise linear. Do you agree with me? Everybody, do you understand what I'm saying? This is also piecewise linear only, but it's infinitely. You put millions of them, then it becomes a circle. Everybody's good? All right. So that's what is happening in the boosting here. And how do we get it? The method is this. So the data is 1 and 5 is a plus, 2 and 3 is minus, and so on. We have, but it so happens the first time I start first time from left to right, and then bottom to top, or top to bottom, right to left. You can do either way, but it starts left to right. Then because when your algorithm package has to do systematically, right? So when I start going here, I get 100% plus. So boom, I stop there. Right? That's my first hypothesis, or first linear, piecewise linear. I'm going to build into a piecewise linear. First, I take it as linear, but then I will split it into piecewise linear. And then, so to the left is 100%, but to the right is, I have 30% error. These are errors. Do you get it? Okay? And these are those points here. So because those are errors, in the next iteration, what I'm going to do is I'm going to boost these weights. These are the D3. D3 is the one that helps us to do the D2, D3 in round 2. Okay, in round 2. So let's not go there. Let's go here, and I'll come back here later on if you want. Okay. So this is what happens. I put this first line. To the left is 100% accurate. To the right is 30% error. So 30% error is epsilon 1 is 30.3. And from there, I calculate alpha 1. Alpha 1 is half of logarithm of 1 minus epsilon 1 divided by epsilon 1. Everybody gets it? I say it from my memory. Correcting like Jeffrey. He's fine last time. That's why I'm saying. See, I'm calling you. Okay? It's a funny three-legged bug there, epsilon. Three-legged bug, right? 1 minus epsilon divided by epsilon. Okay, that's half of that. All right. Everybody's good? It looks funny, it looks complicated, but those guys worked very hard, Fluent and Shapir. They guys work for years to kind of solve these kinds of problems, they can do, you can do your job, that's okay. But you appreciate them for the hard work they did, okay? All right. So, you are going to give more weights here so that it gets a better attention next time. So because you give more weight, some processor you are going to give weight. Okay, let's say you are adding everybody, these guys some weights, extra weight. So because of extra weights, compared, even though there are only 3 observations here, even though this is, these are all getting the same weight, but it won't get same weight. You will take out some of the errors from here, some of the weights from here and assign it here. That's the idea. Okay, so this becomes, so next time when we draw the line, so we want to make sure that in the second time. This is the new line. It's a stump again, left or right, right? Remember that stump, left or right, left or right. So to the right now, 100% accurate, isn't it? But there are some errors here. These are the errors at the second step. Are you with me? Right? And I got this line and this line, but this line is yet to be formed. We will come to that. So this line is we got, they are not piecewise linear, they are linear, actually fully perpendicular. No, I shouldn't have done this as like this. It should be fully perpendicular right now. And this is not there yet, isn't it? Everybody? You understand what I'm saying? Everyone? Anybody has a question? These are the 2 things I got in the second step, right? And accordingly, there is the formula gives me now, there are only 0.21. Epsilon 2 is 0.21 this time. It is reduced the error. But it reduced the error because even though it looks like 3 of them are there, it reduced the error because the weights went down. We took out some of the weights and assigned it to plus to do more weight in step 2. Is everybody's good? What I said? Understand? Excellent. Excellent. So in the third step, what happens? I have exhausted on this axis. I have exhausted on this axis, so I want to go this axis. Is everybody's good? So when I do that, I find that this was to the left here, to the right here, these are the misclassified, right? To the left and to the right here, these are misclassified, and I just want to identify them. When I the way I have to identify, put a line here, then these things are getting assigned correctly. But there is an error here, but it got already cleared in the previous step. Do you understand what I'm saying? Because I'm going to combine them, and then piecewise linear comes out to be like this. If this one got identified correctly in the previous step, second step, this one got identified correctly in the second step, this in the first step, this in the second step. If everybody, I'm sorry, this in the this in the second step. Finally, all of them are combined through, the piecewise linear of this together. Is everybody good with me? The question could be, where did we get this 0.48? Because we have to give a weight of 0.42 here. When we are doing this rule, and when we are doing this rule, we have to give a weight of 0.65. When you are doing this rule, we have to give a weight of 0.92. Not only that, you use what is called a sign function. This is some little bit advanced here. Sign function. Basically, sign function says it is implicating left or right information. The left or right information is given by the sign function. That's what sign function means. To the left means plus, to the right means minus, or the other way. It doesn't matter. Okay, either way. Is everybody's good? The logical structure. Everybody's good? Yes? Excellent. Rajesh?
Yes, sir.
Okay, very good. Avanish? Gautam,
Yes, sir.
Arun.
Yes, sir.
Okay, cool. Gauri Shankar and Arun. Okay, got it. So now you want to know, okay, I understand all these things, I understand the logic. Please tell me, how do we calculate these numbers? That's the question, right? If you do these numbers, then you know how to combine them, you get the answer. That's what this step is about. It tells you this ugly collection of lines, but this is where these bugs are coming. 1 minus epsilon divided by epsilon, right? 3-legged bug. 3 legs are there. Half of this is alpha 2. Alpha 2 is the weight that we calculate, compute the hypothesis weight. How much weight I have to give, right? But the problem is this weight will not give 100%, right? So we have to normalize it. That's what we are doing here. So we create the weights from the errors. We create the weights from the errors. This is the error, remember, huh? Everybody, this is the error. Huh? From the error, we create the weights, but that weight is not summing to 1 as a probability distribution. And also, I know, even before that, we want to use the weights to boost, which one, this is the factor that we want to use it as a factor to weight, right? Which one to boost, which one not to boost. Use the one which are misclassified. These are misclassified, right? Not equal to means misclassified. Equal to means correctly classified. The one that are correctly classified, you take away the weights, and you create more weights for, reduce the weights, not take away. You reduce the weights for those classes that are classified correctly in the previous step. For the next step, you are going to reduce the weights here, add more, boost the weights here. That's what it's called boosting. Boost the weights here for misclassified observation. But these will not become 100%, so you normalize it. That's how you get into the deep values. And so you kind of cycle back again and again and again like this. And then finally, you combine all the linear combination of the models, you get the answer. Is everybody clear on this step?
Yes,
Okay.
sir.
You may still worry about it. It's all good, okay? I still don't know how to calculate it. So that's why I go to this slide. I go to this slide and it tells you, explains all these things to you. And even now, it's only an explanation. So I give you this slide, this workbook. Is everybody's good? And you can play with this. You can see that, these are all formula connected, right? Look at this one. This is a formula. You see what I'm saying? Exponential of E7 is half. E7, where is E7? E7 is this. This is good. Not E7 is this value. Okay, that is a 0.1. But boosting is, yeah, this is the boosted value, right? This is a reduced.
Sir, why are you stopping with the error 3? So why can't you go still to reduce the error?
No, by that time it is 0. By that time it will become 0. See, everything is identified. By 3, by the third step, this is the third step, right? By third step, perfectly identified. So we combine them to create the answer, right?
Okay.
Yeah, you can go on forever, for millions of times. But the point is, until you get a good answer, right? But it so happens in this case it becomes a perfect answer. Where is that guy? The perfect circle, right? Answer. Perfect circle answer. Some other. I don't know where it is, man. I don't know where it is. Oh, okay. The perfect circle answer, you need probably millions. Circle is the answer, but most of the time the points are not billions of points that you need a circle. It's probably very close to circle. Are you with me?
Yes.
Okay. So okay, you say, well, I understand all these things, I put the tabulation, I really want to calculate. So that's where I give you this. Okay, is everybody good?
Yes.
Do you think you will go back and check yourself and, clarify? I think this should be one of the assignments, Supriya, okay?
Yeah.
And in fact, I did add 2 other points and then asked to complete it, okay? Or even going through this, but perfectly clear why you are doing every step is very good, but fun. It is fun. But in the end, in real life, you won't do this. I understand that, but you still need to get the confidence. It's a good idea. Okay. Is everybody good on taking this as an assignment and explore these calculations?
Yes, sir.
Correct? Yes?
Yes, sir.
Yes, sir.
1, 2, 1, 2, 3, 4. Gautam said 2 for somebody else also. Okay, thank you, Gautam. Gaur Shankar? Yes? Okay, cool. All right, so I give you this also. Okay, now let's continue to do this. So there is more calculation. I'm showing you that's fine. And I also showed you the beauty of this. It can even predict a circular collection of observations. Okay, which is beautiful. Which is amazing because it's highly nonlinear. Okay, highly nonlinear. SVM will also do that. You will see with a different approach. All right, so this is about boosting, and then I want to now take you to, okay, should we take a break now? No, yeah, no, another 15 minutes to go, right?
Yes, sir.
Okay, all right. So now I want to run through a case study. How about that? Shall we do a case study? Let's do that. What did I do here? Somewhere I know. Let's see, case study. Let's see. Not this one. Okay. So this is about another data set. Actually, we already did one case study for random forest. This is another. Here is a comparison of. It's basically Adaboost. Forget about it. It's not a comparison. I'll do another case study where we compare. This is a data set about banking data set. It's about a direct marketing data set. They want to know whether there is an impact. Somebody is buying a direct deposit. Okay, direct deposit. So this data set is available in this place. You got to download the bank. It's called the bank data. Okay, bank.zip. You got to download that. One moment. The data set is here. Okay, you have to download it. Can you please download, everybody? Go there, download. So if you click on that one, I get here like this, and then you go to here, folder, data folder. There is also a data set description file. Okay, it gives you description about the data. The data set description is here. You can just copy and paste it in your notebook if you want. Okay, there are 20 variables. Actually, there will be only 17 variables. I think there is a full data set. That's where we got 20 variables. But this one, I think initially is 17 variables. So go to this data folder, and then go to download this bank.zip. That's what we are going to use. Okay, is everybody's good?
Yes, sir.
Please download that. So I'm going to, just hold on. You can do it during the intermission time. Okay, I'll give you extra 5 minutes, 15 minutes, intermission time. So let's do this work. Okay, here it is. So I downloaded it and then I'm reading the data. Look at this one. Are you able to understand this statement here, everybody? Right? You can read that table you can use. N rows, all those things. It works very well. I'm going to do it again one more time. Okay. Add a data. It's a bank data. I can even do unzip command also. Okay. Inside R. So I'm going to redo this one more time. Okay, done. Are you with me? Do you see this, everybody?
Yes, sir.
Good. Yeah, you have to say yes or no because I'm not going to see you because I'm keeping this space for me to work completely now for the next 5 minutes. One moment, please. And then you can do it during the data and other time. I'll give you extra 5 minutes to get back this. And then I want to, there is a package called adabag. Okay, adabag means adaptive, and bagging. Bagging is basically you kind of repeated sampling. Okay, that's a bagging. And it sets aside the testing and train all those things. Now I can copy and paste this in the copy and paste. You can just, you don't have to download, open the data set, you can just read it from a zip file also, I told you, right? So I posted the codes here, and Adaboost is very simple command. I'm going to use only 20 trees, okay, using Adaboost for this variable. Y is dependent variable, which is the direct deposit or not. It's a two class model, and then I regress it with age, job status, marital status, education, default, whether they ever defaulted or not, balance amount, housing, own housing or not, is there any other loans, and so on, all these things. So I'm going to run that now here because I already have it loaded. The data is loaded. Run it here, and so Adaboost is done now. Oh, it's still working. You see this red circle? It's still working. In the back. What did you say? Yes.
You said that before boosting we need to do the random forest. So here we are not doing random forest.
No, I did a random forest one. That is a separate exercise. Here is another example. I'm still working on a case study to focus only on Adaboost.
Okay, so every time we not, it's not required to do random forest.
Whatever you want, you can do. Adaboost, you can do a random forest, or you can do SVM, or you can do all of them and compare the results and so on.
Okay.
Okay, it's not that you have to go through the other things before you come to the next topic. In application, it's everything is separate. Each of them are separate. There are 155 separate machine learning algorithms out there. Okay, so we are only going to talk about only few of them, 5 of them, which are considered to be the most important. Okay, and in your life also, you just concentrate on that. That's my suggestion. Okay. Of course, now neural network has also developed into deep learning. That's a separate issue, but nonetheless, it's only again neural network. We said we are going to use neural network. Okay. That's one of the 5. So it even plotted my. Let's look at this one. What is this happened here? No package called a tree. We'll come to that. So I copied and pasted everything. That was the problem. Okay, it ran everything except we'll go back to. Let me explain everything.
Oh, I accidentally
So I actually did only this model, I thought, but it didn't. No, it took everything. So I'm going to copy this alone. It did everything. I don't want to go to do it too fast, because I want to explain a few things for you. So I do this model again. I'm going to redo it. Adaboost is getting done, and Adaboost is an object. Remember that. So always when you create an object, what is inside there is a very important question. And then it is doing data is added data, which is what I downloaded it. Added data is bank data. We can find out what it is, and these are the variables we have. And then boosting, yes, true. M final is now 20 trees only. We are going to use it. Coefficient to learn is used what is called the Brayman method. There are different methods. Okay, Freund method, Freund and Shapiro method, Brayman method, and there is another method also. So I want to see what is there inside Adaboost. Okay, so you can see there is a call there, which is basically a formula type. What is the call made? Just check it out. Adaboost $call. It says the function. Okay. Whatever the function we use, boosting function. Adaboost $class. These are the classes, right? Yes or no, yes or no, yes or no. There are, and then I want to know what data, how many data is structured, added data, right? Oh, added data. So it says there are 4,521 observations are there, 17 variables, and these are the variables, and these are the levels, or factors, or integers, and so on. Is everybody good?
Yes, sir.
Okay, good. Let's continue to do that. Okay, I can explore more things, right? Because I said these are the object members, right? What are they? Adaboost, right? These are the objects. So weights are there, properties there, variable importance is also there. You see that? So Adaboost dollar importance, it is going to give me the importance levels. So obviously duration, there is something called duration matters. Huge important variable, okay? For example, right? It's not in plot form, but it's, you can still see this. And then, you know, the probabilities it calculates the terms and trees. So let's see, what does tree mean? You know, maybe Adaboost dollar trees, maybe first tree. This is what the first tree is. Do you understand what I'm saying? How I got it? Everybody? Understand?
Yes.
Okay. Please be louder. Yes?
Yes, sir.
Yes.
Okay, thank you. So let me explain more. So I can also do summary, you know, Adaboost. Summary is a very common term you can always use in R for any object models you create. Summary, Adaboost. So it says it's not that great because it tells you, you know, how many votes are used, how many properties are used, how many classes are there, 400 to 4,521 classes are there, importance variables, 16 variables, importance are calculated and so on. But let's get a little bit more detail in terms of understanding it. So I told you this, you know, the 20 trees are created under the trees object member, okay? And the weights are given here. So I'm going to important variable evolution. I'm just going to say, you know, the predict Adaboost, add data. You can give new data here, then it will be your prediction for the new data. So let's just see what this tree looks like. Okay, how about that? Just see how we can plot it into a tree form, right? We know how to do the trees, right? How to look for the trees. So let's do that. So there is no package called tree. So tree is tree. There's no library tree is not there. Okay, so there's no package, but nonetheless it is available as a plot. I don't need the tree, so it's part of a standard package, I guess. Okay, because I got the zoom here, I got the tree here. So this is what the tree looks like. First tree. There are 20 trees like this. Is everybody understand what I'm talking? The whole set of observations are there, left or right only always. So remember that. Huh? So P outcome is failure, other unknown. These are grouped. No, these are the group. What are the values? Let's go and see that in the web page. Let's go and see the web page. P outcome means what here? This one, outcome of the previous marketing campaign. Categorical, failure, non-existent, success. Okay, it failed, it succeeded, and doesn't exist for a particular individual. Are you with me? So that is, you know, is the first variable. That's the first variable. It's coming up. Yeah, that is the first variable. You know, that's coming up. So on the left side, okay, on the left side. On the right side is contact, telephone, and unknown. That is split here. P outcome is split here. On the base of P outcome is split here. And then the left variable is month. Okay, campaign month. And then the duration here. And so on. Okay. So my point is now you can actually see each of the time. This is done by, remember, Adaboost method. Okay. And this is how you get it. You can use this to predict also, you know. You can do all your stuff. So that's how you run your Adaboost. Are you with me? Or am I going too fast? Because we are going to repeat this again anyway. Or we might repeat for the same data or for a new data set in the lab. Okay. Everybody's good?
Yes, sir.
Okay. Any questions? You are good? Everybody's good? Gauri Shankar?
Yes, sir.
The codes also in the chat area, okay? In the codes and in the X, it is available in the slides also, in the PowerPoint slides. So the next, when you come back, I want to cover how do we use Adaboost for multinomial and multiple class, and also logistic regression for multiple class. Are you with me, everybody? When you come back, I want to do that as another case study. We will use it with iris dataset. Okay, iris dataset is 3-class plant classification, right? 3-class. Everybody's good? Any questions? Arun, are you there? Okay. All right. Have fun time drinking your tea. We'll meet in 10 minutes. Okay. I hope you will run this, what I gave you. Rerun it yourself and check all those each lines. Makes sense, makes sense. Okay. Good. One moment, I think I'm getting noise. One moment. Okay, tell me, loud please. Avinish?
Yes, sir, it's clear.
You're good, okay. All right, everybody, we'll come back and start in another 10 minutes, around 10 minutes. And I will go through multiple class problems where we can use random forest or logistic regression or the Adaboost. Thank you. Hang in there. Stay put.
Okay. So stop recording.
Thank you. Oops. Resume. Okay. Did you switch on recording, Supriya?
Yeah.
Okay. Thank you. That's a good idea. So I take the iris data set. What is the iris data set? Everybody, can you recall? It is the Fisher data which has 3 classes of plants, right?
Yes.
Virginica. What are the other things? Virginica.
Sentosa.
Sentosa.
Senista, I don't know. The other one, I don't know. I know only Sentosa.
Okay.
Sentosa.
Virginica, Sentosa. Okay. Let's see. Sentosa, 1 second. I think we can figure that out. No problem. I think it is data is available in R. We can just print it also. That's an example. Head, iris. Okay. It is Cetos. Okay, I have to do a table.
Table of species.
Iris dollar.
Species.
Versicolor. Setosa, versicolor, and virginica. 3 of them. So there are 3 classes. If you want to predict one of those 3 classes, we are talking about a multiple class problem, right? For the first time, you are coming to, you have seen the iris data set. But I haven't shown you how do we think about multiple class problems. So I'm going to use this as a sample data set to do 3 models. One is logistic regression approach, the other one is Adaboost, and then the third one is XGBoost, which I'm going to teach first. Okay, sounds good? Excellent. So that's our plan for the rest of this half of this session today, and we will see if we have more time. We can do other things, but okay. So what I want to get your attention is the following. So you can do Adaboost. We don't have any. It so happens that it doesn't overpredict. That's the idea. Okay. If people generally say Adaboost doesn't overpredict. But if you use neural net, it's a worst case scenario. Okay. Every observation will eventually become as if you are able to predict, because you are using that many number of parameters, right? You remember that issue? You are using that many number of parameters. So how do we handle this issue of, for boosting also, should we not use okay, I did. So should we not use a way to control the number of parameters? The number of parameters is always a problem, right? Because you will become greedier and greedier because you want to do your best job for prediction. You will end up adding more and more and more parameters, which means more and more you are adding more complexity. Okay. So how do we handle that? We know the bias variance trade-off is the way to address that. You all agree, right? We know bias variance trade-off will help us to control the complexity issue. Are you with me? Why am I going there? Because I already told you I'm going to talk to you. We have logistic regression method. We have random forest method, and then boosting method. In the boosting also there are two methods. I'm saying Adaboost and then extreme gradient boosting. And extreme gradient boosting is going to kill the model building because it's going to predict very perfectly. But that means the more the perfect, that it means it's going to be possibly bad for the new data. Right? You understand what I'm saying? The more the perfect is going to be possibly bad for the prediction of new data. So how do we control? The control method is complexity versus predictive error. And wherever the complexity, the predictive error starts increasing, just stop there. Don't increase the number of parameters. Now, number of parameters is represented as complexity. Everybody is good?
Yes, sir.
So far. So the point is, I'm going to start with the process because your optimization is a function that involves this addressing this number of parameters issue as part of the optimization. So let's review this one. So here is there are different logistic regression method. So what we want to do is that, if you look at this one, this is the logistic regression method, loss function. And as our loss gain function, you may get worried about that. But basically, if you use this model, and logistic model, then this is the error in the prediction. Are you with me so far, everybody? This is the error in the prediction. yi times logarithm of, this is the probability of yi is equal to 1. This is probability y is equal to 0. That's what it is. Okay. So that probability is weighted by these corresponding values. yi times ln 1 plus exponential of minus w prime xi. That is what the logistic expression is. And the plus 1 minus yi. Here is yi. It's 1 minus yi. The complement of, there is no minus here, plus here. Okay. This is your loss function, but we are going to not just leave it as it is, but add the lambda times, double bar w double bar square, which means it's norm. Please write down the word norm, N-O-R-M, norm. So lambda times the certain proportion of the parameter. Norm refers to sum of squares of the parameter values. These are our parameters. W1, W2 are parameter values. Do you agree with me? Because that's why it is here, the linear combination here. W prime x means the W1 xi1, W2 xi2 like that. Are you with me?
Yes,
huh? Correct. Yeah. So what does this mean? This means W1 square plus W2 square, W3 square like that. Just because you put a square here. Okay. If you don't put a square, okay, then you just say square root of W1 square, W2 square, W3 square, which is the usual Euclidean norm. Euclidean distance. So what happens as you increase the number of parameters here? What happens is this norm square increases or decreases as the number of parameters increases? Do you understand what I'm saying? This norm means what? Norm square means what? Norm square means that is W1 square plus W2 square, W3 square plus W4 square and so on. If there are 10 parameters, then W10 square. Okay? So each of the term is, because it is a square term, it's positive. Take a look at me, and talk to me. Is each of the term is positive? So some of the squares of positive values will always increase as I put more W's, right? Yes? So this is a measure of the complexity. But we don't want to take it as it is, but we take a proportion of the measure of complexity, not the full value. Is that okay? So some way we want to address that as part of the loss function. What does this mean? As the number of parameters increases, this is going to more and more weigh down the loss, because otherwise the loss will explode, increase. Okay. In other words, if you don't have this, okay, if you don't have this, your error will go down very fast. But because of this, the error will not go down. After a while, it will start going up because of this. Are you with me?
Yes.
In other words, the predictive error, bias variance trade-off, is represented by some kind of expression like this. Do you agree with me? Because this will increase. This is the error. This is the error will increase because of this after a while. Yes or no?
Yes. Yes.
Everybody has to get this idea. In other words, by adding some kind of a proportion of sum of squares of the parameter values, you can have control on the number of parameters while minimizing the error. That is a very simple statement. And that statement is captured in symbol like this. Everybody gets it? Very, very important. Do you agree? It's a good idea. So when you optimize the loss, this is called loss function now. When you optimize the loss, you are already factoring into the number of parameters. And that is for logistic regression. And you can do not just W1 square, W2 square, but you can also do absolute values of W's. That's what this one means. Norm 1, L1 norm. This is called the L2 norm, because it uses square. But here instead of square, you just take absolute W1, absolute W2, absolute W3, and so on, absolute W10. Everybody gets it? That is a different type of norm. Okay? Again, we are kind of taking some kind of weighted value of that one. Do you see what the difference between this and this? This is L2 norm, this is L1 norm. So your loss function can be either this or this. In fact, you will say later on, why not we use both? In XGBoost, we use both. Everybody gets it? Okay? Everybody gets it? That is true even for linear regression also. This is linear regression. But when you use it like this, it's called bridge regression. Okay? Everybody? You understand what I'm saying? Please ask question. And also, this is called L2 regularization. We regularize the loss. That's the word people use it. L2 regularization. So if this is L2 regularization, once again, if that is L2 regularization, I'm going to do something. What is this, you think? This one. This one is what? If this is L2 regularization, this is also L2 regularization. What is this one, you think? Anybody? Huh?
L1.
L1 regularization, because the power is 1 here. In the W1 square here, it is absolute W1 here. W2 is plus W2 square here, but plus absolute W2 here, like that. So that is called L1 regularization. I took it out so that you kind of can imagine what it would be, and it is correct. Are you with me, everybody? These are the terminologies you have to learn. So they will ask you probably in the interview, or even you will have to think about it. It is always important to regularize your loss function. Everybody is good? It is always important. Everybody, okay? It's always important. All these things are brought into XGBoost, okay? Now, let's go the slides. I'm going to open up the slides. Is it too theoretical for you guys? You can understand. You're all engineers, right? You can understand, right?
Yes, sir.
Okay, thank you. Even if it is theoretical, you just see it 10 times, it becomes, oh, you know it. You know what I'm saying? It's just repetition. Intelligence is just repetition. If somebody tells you anything else, tell them, okay, go home, man. Take a hike. Intelligence is just repetition. Believe me, it's like a parrot. People would like to say something else. No, I am better than you. I am more intelligent. Go home. Okay, it's just repetition. Understand, everybody? So you can all do it. That's what I'm trying to say. So let's No, this was developed by a graduate student. Can you believe? A lot of people tried to do PhD, and this became so popular, so big deal stuff. I wanted to get this. Let me see whether open. Why is that I'm not able to open?
Control click, sir.
Control, yeah, that's what I do usually. Control, click. Okay, yeah, it did come. It did come. Thanks a lot. It's given by the producer, the original thinker. So I love this because of that. Okay, you know, always use the original thinker's notes. Oh my goodness, he has 228 slides. Man, look at this one, right? 128 slides. It's almost like a book. But it's fundamentally it changed. When it came, initially, 10 years back, randomforest was winning in competitions.
Oh.
And then 7 years back, boosting, Adaboost and gradient boosting was winning in competition. And the last 5 years, XGBoost is winning in the competitions, or SVM, or combination of things. Okay, but XGBoost. So that's the power of XGBoost, and I will definitely encourage you to. This is a graduate student, Tong He. I know I definitely encourage you to look at this data again and again. Look at this one: basic walkthrough, real-world application, model specification, parameter introduction, advanced features, Kaggle winning solution. Happily, he says winning solution. Of course, it's true. So you all learned linear regression, logistic regression, K nearest neighbor. I didn't teach you this one. I will have to teach you this also, nearest neighbors. Okay, we'll do that. You will learn this support vector machine. You learned so far decision tree, random forest, gradient boosting machine. Boosting machine, Adaboost, but the gradient boosting machine is the next version. But since it is implied in this one, I will not go into separately this one. Extreme gradient boosting is what we'll talk. Neural network is another one. These are all the ideal things to try. Okay, so I'm not going to do all these things. Let me just go. It is easy to install. Efficient. It's accurate. It's flexible, feasible, and so on. Tunable parameters. ... All those things don't bother me right now. Okay. So here's a lot of stuff here. He is explaining how you can do all these things, but let's not worry about this for now. I want to go and explain the logic. Logic is first. All these things don't bother me. Wait. 4. Okay, here it is. So root mean squared error for regression is this. This is the regular regression using root mean square. Okay, everybody. Log loss is this one. This is what your log loss, right? For the binary classification. For multiple binary classification, we use M log loss, which is same as entropy. Everybody, you understand this one? It's average entropy. Everybody gets it? This is average entropy. Do you understand what I'm saying?
Yes.
Right.
Yes, sir.
Yeah, you have to think, when I say something there, when I say something new, is there a connection there? This is average entropy for multiple classes. So he is using the entropy basically to do the problem solving. So this is what your T is the number of leaves, because it's a tree, right? Okay. So T is the number of leaves, and then the weights, the L2 norm of the weights, and then a proportion of that is taken as added to the number of leaves times gamma. Number of leaves is T, gamma is another proportion factor. So what are the number of variables, number of parameters here? Gamma is one parameter, lambda is another parameter, T is the number of leaves. Each one of the leaves is a parameter, right? And the weights for each of the parameters is Wj, the leaves is Wj. So there are T here, T plus T, 2T plus 1, 2T plus 2. 2T plus 2 is the number of parameters in the tree. Are you with me so far?
Yes, sir.
Okay. So the objective function is this is this is what is called the regularization, and so we add the regularization, that's called sigma, right? Here, look at this one, sigma, right? So he is using two parts. Is the number of parameters itself is another weight he is using it besides the L2 norm. See, I didn't show that earlier. We didn't use this as earlier. Only L2 norm we used. Okay, but L2 norm plus the number of leaves also matters. Now he says we will use that. Okay, you can do many different ways. You can weigh down the loss function by bringing in a function of the parameters. Okay, so the objective function is the likelihood plus the regularization. So that is the objective function. You see the omega, this is the trees, F1, F2 are all trees. And I will review this again second time, don't worry about it. But you understand up to this, the objective function is loss function evaluated at the previous iteration plus the rate at which it is decreasing, the loss decrease, L, right? The derivative, when you take the derivative with respect to yi t minus 1, so because you added the previous tree, how much, this is the reference to basically, instead of derivative, you can say change in the loss. Instead of saying derivative, you can say change. Because you added the previous tree, how much change in the loss happened. That's what GI is. The second one is the rate at which the change is happening. That is the second derivative. So it's also called velocity. Are you with me so far?
Yes, sir.
I used the word velocity. So the rate at which the loss is changing, because I bring in a particular tree in the previous step. And by doing this, at what rate, the velocity at which the loss is changing. Those two things we are going to use to solve the problem. Are you with me? So when you do that using Taylor series, have you heard of Taylor series expansion? You all heard of it? Anybody who didn't hear? Anybody who did not hear Taylor series expansion? You did not hear. Gautam, you didn't hear. Rajesh, you didn't hear. You guys are not engineers? I'm serious. I'm sorry. I meant, I thought maybe you're a manager, MBA guys. That's why I asked that question. Are you engineers or not engineers? Huh?
They are engineers.
Engineers in what sense? See, MCA may not have, I don't know. MCA also, in BCA, you will have calculus, right? You all took calculus, right?
Yes, sir.
So there is a Taylor series expansion. In other words, every function, however complex it's a function, as long as it is differentiable, okay? At any point, you can evaluate the value of the function using a series of values which are a function of derivatives. Okay, that's basically it. At any point, you can calculate it using derivatives, and giving some weights to the derivatives and so on. So basically, it's an approximation of a function. Okay, basically it's an approximation of a function in evaluation. However complex the function is, even if you don't know, well, I don't want to say the word don't know, but as long as it's a differentiable function, it's fine. Okay, you get it now? That's exactly we will use. We will approximate this objective function using the Taylor series function. That's what this one is. So here it says the second order Taylor approximation. Okay, Taylor approximation, and this is the expression. So very important point is, by adding at every stage, so the objective function, the loss function at time t, step t, is dependent on what is the particular tree I added to. See, remember there are lots of trees we are going to add into the forest, right? Lots of trees we are going to add into the forest. It's also a forest. XG boosting is also a forest. Do you get it? But the point is, the question is really, what are the trees I have to add every time, right? There are so many possibilities are there. Which tree I should add? Is that a good question?
Yes, sir.
So if I have 10 trees I have already done, the next question is, what is that 11th tree I have to add, right? What we are saying is, the 11th tree, this is the 11th, this is the 10th tree, t minus 1 is 10, 11th tree is this. And I add the 11th tree, what happens to the objective function? But our purpose is, objective function is to reduce the error. Objective function is basically error, correct? Objective function is our error in prediction. So we want to find that tree, you know, ft is that tree. Remember that, huh? ftx is that tree. We want to find that tree. This reduces this objective function at the 11th step, right? But that tree is weighted by the rate at which the objective function is going down. That's what GI refers to. That's a change in the objective function. Please write it down. GI is change in objective function. HI is the rate of change in objective function. GI is change in objective function at the previous step. At the t-1 step. HI is rate of change of the objective function at t-1. See, that's what the second derivative, that's what it means. So you can call it as a change instead of saying derivative. So using that and Taylor series approximation, I can rewrite it like this. Everybody gets so far? Is it okay? It's easy now, right? What I explained. Correct, Avinish?
Yes, sir.
Yes, sir.
So this is fundamental. You understand what is GI is? GI is at what rate the change is happening in the error, predictive error. That's what the objective function is, the predictive error at the previous step. HI refers to at the previous step at what rate GI is changing. That is the rate at which it is changing. The reduction in the error is changing. And you use those two things and then, you know, weight by the those are the weights you attach to the new tree that you want to add. The new tree is FT. Do you look at this one? New tree is FT. That's what you want to add to the forest. FT is new tree you are adding to the forest. Everybody gets it?
Yes, sir.
Okay, good. So you compute this one, and if the reduction stop, as the reduction, what it means is that after a while it is going to keep increasing bigger and bigger because this is the regularizer, right? Right hand side, omega Fi is a regularizer due to adding Ft. In addition to previously it was up to Ft-1. By adding the Ft, now you calculate also this one, so it's going to increase, right? So you are going to optimize. You know, your loss is managed between these two forces. That is the regularization versus the reduction in the error. It is managed by those two forces fighting in opposite direction. Everybody understands?
Yes.
But the benefit is you are able to address the complexity in one loss function. You don't have to do it separately, the U curve. You get it? Everybody?
Yes, sir.
Okay. Now, but you know, if you look at it, the first part is a constant. This doesn't change. This is a constant term, okay? So we kind of remove that, and so the objective function becomes only this part at the teeth step. At the teeth step. So here is an example. I'm going to go to another presentation deck. I think that is a beautiful example. Tree building algorithm. Okay, let me open the other one. Up to whatever I explained is good, but you know, I want to open another one. Okay, here it is. Takes time to load, you know, because of graphics, I think, yes. Model and presentation G.
They won't ask.
Okay, maybe here. Not this one. Let me close this. We are ready. Controller. One moment, please. I'm trying to locate my XGBoost notes in relation to it. Something is missing. This one didn't work out. Okay, maybe. Okay. All right, let's see whether I have that notes here. Okay, yes, you can see this. Everybody, please take a look at this one now. Are you ready? I can lost you a little bit. So you see this one, it is in a printed PDF. So the same thing here. Do you see this one? The loss function is written as the previous predictive error. That's what loss function is. Previous predictive error due to adding the previous tree to the forest t minus 1 plus the new tree that we want to check it out. Whether that tree should be added or not will be checked out by calculating this expression. But when we, this is the tree we add, but weighted by the rate of change of the previous tree addition in the error, right? Rate of change in the rate of change is same as change in the reduction in the error in the previous step, plus at what rate it has been decreasing between the previous two changes, for example, right? That's what the HI refers to, which is the second derivative. And that one will be, in this case, we'll use the word, ft square, and here we use ft, and here we use ft square, but they have different weights. This is the rate of second, the velocity at which it is decreasing. This is the rate of change of decrease in the loss, in the predictive error. Okay, plus the regularization. Due to adding ft, how much is changing this regularization function. Okay, remember regularization function could be we said it can be two parts. Here it is the two parts. That is number of leaves weighted by gamma plus this L2 naught weighted by lambda. Okay, so that is the regularization and how much value you get there. You add that to the reduction in the error, and that is what your last function is at time at tree t. T is the suffix, right? The teeth tree, T, S and T, right? That teeth tree. The previous one is T minus first tree, T minus 1 to tree. The previous one is T minus 2 to tree, T minus 2 tree. So there are a number of trees are getting added, and every time we bring a new tree, we check out this value. If it reduces only, we add. If it doesn't reduce, it starts increasing, we stop. Are you with me so far? So that is the approach to use it. Here is an example. Take a look at this one. So in a family, there are 5 people. There's a boy, there's a girl, and then there's grandpa, grandma, and the boys and girls' mom. Okay, that's the family we have here. In that family, okay, so we have these variables, age variable, gender variable. Okay, listen very carefully. So age is less than 15. This boy is less than 15, girl is less than 15, let's say, okay? But grandpa, grandma, and mom are not going to be greater than 15, right? Less than 15, right? So 2, 3, the age is less than 15 refers to the sample 1 and 4. 1 and 4 is, I think it's not correct, It should be girl. I think both of them should be girl. Maybe that's what this girl means. 1 and 4. Okay, this is a girl. I thought this is a girl. Okay, this is a girl, this is mom, right? So there is something here. I would say it should be 3. Let me write it down. One moment, please. Comment. I'm going to write it down. It should be, isn't it? 3. 1 second. Property is too big. I want to reduce the size. I don't want 2. 1 point is good enough for me. Okay, it should be 2. And above, is there any question?
No, sir. Correct, sir. 1 and 2.
And this one is age less than 15. No, that means 3, 4, 5. Let's consider 3, 4, 5. Let's include 4. Okay, instead of 2. Everybody's good? So accordingly, this is going to change this number here, right? These numbers are going to change. I'm sorry about this. Let me check, is there any other definition? They mean something else, I don't know. Otherwise, this is the way it should be. And then, if it is, this is about, the interest to play games, right? So age less than 15 versus age greater than 15 makes sense. And then for the leaf 1, which is male or not, right? Yes, male means G1, H1. If it is not male, then we are talking about I2. Oh, here it is G2, I2, G2. We are talking about I2, leaf 2, right? No, it is about leaf 2. It's not about gender. Okay, it's about leaf 2. Okay, this is leaf 1, leaf 2. This is leaf 3. Okay. But anyway, so let's consider, in our own way this correction, and I'm kind of curious to know what the book has. I will go back and check other publications. So now you have G1 for this leaf. You have a G1, right? The change in the loss. G4 in this case it is G2, H2, H1, H2. Here it is G3, G4, G5, H3, H4, H5. Everybody's good. The objective function is, it turns out to be like this. In mathematics, it turns out to be like this because there are 3 leaves. 3. T is the number of leaves is 3, so 3 times gamma, and Gj squared divided by Hj plus gamma lambda. H refers to H1, H2, H3. Here, okay, H1, H2, H3. G1, G2, G3. So you can calculate this. The smaller the score, the better the model is. Do you agree with me? The better the particular tree is. This is This is the Tth tree. You have added the T-1 tree before. You are going to check it out whether this is the right tree to add. Now, if it goes down, and if multiple trees are going down, then you want to take the smallest, the highest reduction in the score. Okay, and you will keep that as the tree. Do you understand what I'm saying so far, everybody?
Yes.
Okay. One person said yes. But as I said, it's just a repetition issue. It's just review this again and again. You'll know. You will be. You'll become expert. So that is how we build the tree. So this is all about how do we build the tree, isn't it? Adaboost also I did the same thing. How do we build the tree? Everybody, right? This is again how to build the tree. Next tree, next tree, next tree to add to the forest. That's what the idea here is. Okay. Everybody's good? Any questions so far?
No, sir. No, sir.
And how do we know all these G values, H values? H is the derivative, second derivative. How do you know it? Because of the Taylor series. So it's well known. Okay. It's not anything new. Okay. So using that method, we can calculate, continue to modify our, what is the tree to add to the forest, what is the tree to add to the forest, and so on. And this XGBoost does a lot of other things. It parallelizes the tree building process. It also works with it also knows how to work with the sparse data. So a lot of improvements they did. That's why it became very, very popular. Okay, it is popular even now. Even now, it's very popular. Okay, and it won a lot of competition. In the competitions, it won. So here is the kind of pseudocode here for sparsity, and then you have also here pseudocode for regular data, raw sparsity versus non-sparsity data. So the point is, don't get worried. Oh my goodness, these are all going over the head. What am I going to do? You are not going to do anything like that. You are going to use the package. But you have to believe in the package. That's why I explain all these things. Okay. All right. Now there are lots of different gradient boosting methods are there. Here is you can see besides XGBoost, there is also RGBM, scikit-learn, H2O, Spark, MLlib, PGBRT. All these things uses some kind of a boosted systems. Okay, XGBoost is one of them. There are a lot of different boosting methods out there. Some variant, you can introduce some variation. You can call it, as long as it beats lots of things, you can call it your name. That's true. That's also possible. Okay. Now I did that. So let's go and do some work about that. Okay, let's do some work with actual data. Is it a good idea?
Yes, sir. Yes, sir.
Okay, all right. Let's do that. Yeah, this is what I already notes. Do you see this one? I already have notes. This is what I wanted to open, but I didn't open it. Oh, so let me review this again one more time. Huh? So here it is. Input, there are three variables are there: age, gender, occupation. Okay. Now, does the person like computer game or not? That's what we are trying to build as a prediction. Okay. So age less than 15. So now you see this one, right? The baby girl is there. This is a better one. Baby girl is there, boy is there. Huh? Okay. And here, mom, grandma.
So that mom, and this one is the girl.
What is it? I'm sorry.
The three of them.
Yeah.
That is actually the one in the sequence. Actually, the second was the mom. The fourth was the daughter. That's why it was G4 here and G2 on that side. I1 equal to.
This is I don't remember. Oh, for the age they let me go back and check it out. I thought it was confusing. Let me check. Okay, here it is. No, not this one. Yeah, let's see.
You have a daughter.
No, I put a ponytail.
My daughter was
Okay, here it is, right?
Yeah, that's why it was 4 and 2 the other side.
Oh, this is mom, you think?
Yeah, this is the mom.
Okay,
And,
fine. That is fine. Maybe because of the hair cell, maybe I don't know. Okay, fine. I was confused. I thought yeah, this is girl. Okay, good. Then we don't. I shouldn't use this one. Thank you. That is better. I don't want any error in their write up. I was confused. This I thought is a girl. Okay, now let's go back to this one. It's a lot more clearer here. So what we are saying is so the tree 1, this is tree 2, okay? This is age and male only, 2 variables only we use. Use computed daily or not is not used here. But in this second tree, there is only 1 variable is used. Remember, you can devise 1 variable or 2 variable, 3 variable, or a combination of them. I mean, randomly you can select those numbers and so on, but usually you fix the number, right? Number of variables you select. But here in this case, we are saying a different collection of variables. Okay, age 15, the boys and the girl, and then this is all the elders here. Okay, and these two they become the leaves here, 2 leaves here, and then there's 1 leaf here if it is greater than 15. Now, in this case, if you want to evaluate a tree for a particular observation, if the score is 2 plus 0.9, if you combine these 2 trees, right, 2 plus 0.9, right, for the boy, it is 2 plus 0.9 here. For the grandpa, it is -1 here. This refers to, for all the people with the age less than 15 and male or not, they don't play at all. Okay, they don't like to play the game. Basically, don't want game. This boy wants it all the time. A girl says, okay, I'll play once in a while like this, right? That's what this means. If I use daily computers, boy and grandpa use a lot compared to, they don't use daily, okay? That's why this is less, 0.1 here, right? The girl, even though she is, less than 15. So if you want to use these 2 trees, how do you calculate the score? This is how you calculate the scores. Here is 2 plus 0.9. It is for the grandpa, it is -1 plus 0.9. Okay, where is the 0.9? 0.9 is coming here, and the -1. 0.9 is coming here, and -1 is coming here. Okay. Now that is how to combine the trees, right? We continue to combine the trees. So here is the YA, the predicted value of using K trees, capital K trees is this predicted value of. That's exactly what we did, right? Just now. And here is the how a single variable affects depending upon the various states of the variable, right? So how can we learn function? Define objective function, optimize it. Here, consider the regression tree on a single input, and before 2010, 3rd March 2010, year 2010 versus year 2011. Before March 20th, he has less interest, but after that he has more. The model is to split on time. Okay, time is the one that variable is time here. Okay, time is here. We are using time to figure out when the time is less than March 20th. There is less yes, he is interested in listening to romantic music is less. Okay, he is not interested in romantic music. That's what this means. So why there's a lot more score. Okay. On the other hand, after the March 1st in 2011, the score is decreased. Okay, it is decreased here, because he met a girlfriend. When I met my girlfriend, before I met that, the score is less. For some time after I met my girlfriend, there's an increased interest in romantic songs, and then after a while it tapers off and it decreases, but still it is above than this one. So this is where trees are created, right? Where to split in terms of time, using time here. How to split, how to get the values. This is the value predicted. This is the height, right? Interest. This is the interest. The vertical axis is interest in romantic music. So So what we are saying is that now you divide the tree here just using one variable and add the tree. But by adding the tree, you want to check whether the overall loss function is, increasing or decreasing or stabilizing, right? So you cannot use too many splits, because if you use too many splits, just using only one variable, your sigma f, the regularization is going to increase. Agreed? Because your number of parameters increases. If you use too less, your LF is, too high. In other words, you can continue to improve. The right thing to do is, split it at the right place. The right place is this part. This is the right place, and then in this case you are saying up to this is this interest, suddenly interest increases, and it goes up to this. So this is just a one example. This is another example I have. There are two examples I have given you. Okay, basically. My point is, your objective function is the loss function due to the previous added steps, and then you want to add continuously. Once again, it is here. Yeah, here it is. Okay, the previous steps, objective function is previous step. Here, the loss or the reduction in predictive error due to the previous tree, plus you want to find out what the next tree is. You keep adding and check it out. But when you add, you have to check these calculations. When you add, because this is our original function, you are using Taylor series, you are kind of approximating it to up to this level, up to second derivatives, and these are the second derivatives we are calculating here. So how fast the rate is changing, this is the rate of change in the tree gain, the tree they are gaining in accuracy, and you compare this again and again, and they select the one that adds to the decreased loss, and it doesn't, the overall loss doesn't increase. Okay. It is decreased loss, and overall does not loss increase, because this regularization will increase if you keep increasing forever. So that is what we are talking about here. So here is again the same problem revisited here for the loss function. This particular loss function, we calculate that there are three leaves of the gamma 3 plus gamma lambda plus 4. Okay, that is the square of the word, right? The score. This is square 0.01, this is square 1. That's why the second derivative is coming into play here. Okay, that is lambda is for the second derivative, the square of the parameter value, and the gamma. So this is our actually this is the regularization part. Okay, complexity part alone. This is how we calculate. So there is a way to calculate it. There is a way to justify it. What to add, what to stop. But all those things are taken care by your package. So if that's the case, can we apply the package and solve the problem? That's what we are going to do now. Are you ready?
Yes.
Okay. All right, so this is the one I'm going to, there are a few different things, and as we do the lab work, you will see we will do some Kaggle problems also. Okay, so let's do this example. The data set is iris data set. Okay, we are going to take 75-25 split. So the example I'm going to run through is this one. Please note it down for your purpose. I want to share with you this example. So in this example, we are using iris data library XGBoost. Okay, and species is iris. We already saw that, and you have to give the label as integer value. Okay, that's the only way it will work. Okay. So why don't we do that ourselves, compare. And then we are going to compare this with, what is it, random forest. XGBoost with the Adaboost and random forest. Okay, possible, right? Let's see. Okay, so I want to do this step. I already have downloaded it, so it shouldn't be a problem to me. There's a package called XGBoost, so I have to install that. So something happened to my old package, so I'm going to install that. Okay, it's done. Now I do library XGBoost data iris. I say it is there. Okay, that's all it says. So if I do this one head, so that's what it is. Okay, so it is a 3-class problem. Let's do XGBoost for this, and then we'll compare that with Adaboost and also randomforest. Okay, logistic regression. All right, so we want to label your dependent variable as integer. That's very important, and then we want to remove these species after we label it as integer. Are you with me?
Yes.
Okay. So if I do label, I get 0, 1, 2 because 3 classes are there. Are you with me? 0, 1, 2. 0 is our first value. Everybody?
Yes, sir.
Okay. Then I want to take 75% as training, 25% remaining. That's what minus means. Okay, minus training index means remaining goes into testing, and then label, test label is test label, train label is train label. Okay, so let's do that. So what is how many samples are there? 150 is there. Dimension of train dot data, right? That's what it means. 112 went into there. Test dot data is the remaining should be there, which is 38. 150 is total. Okay. All right. Now comes. So we have to do. We have to prepare the XGBoost is a little bit trickier. Okay. You have to prepare the data matrix. Okay, in a particular way. So, and it also helps to create data matrix. The train XGB.train is going to be put into some kind of matrix using this kind of function. Is that okay, everybody? You just have to follow that method because they structure the data in a particular way. Okay. Let's see whether we can view that XGB. View XGB.train. Let's see if we can do that. We cannot do that because it is a different class. It doesn't work with the view function. Do you understand what I'm saying? If it is a regular rectangular data, you can do that. But XGB data is in a particular form. It's internal class. It's a different type of form. Okay, inside is there, but it is structured for XGBoost functionality. Okay, so but it is done. It is working there. You know, you can see it is there. The structure is there. So XGB, external pointer of class. Okay. Now, because they optimize it for the structure of the data, they optimize it for parallel processing as well as spots data. Okay, representation. Parallel processing as well as for spots data. So now number of classes, we need to define the number of classes, and then that's the end of the story. Afterwards, you can fix the parameters. You set up the parameters. Booster is GB3, ETA is the amount of reduction, right? You want to test, it's a kind of stopping rule. 0.001 when it is not changing below that. When it reaches this, just stop. That's what it says. But the maximum depth is 5 per tree, and then there is a gamma value. Remember number of leaves, that's gamma weight is 3 units. Subsample is every time we take 75% of the rows. Column sample by tree is 1 variable. We are taking only 1 variable out. Half. The column sample by tree is 1. Oh, that means all variables. Okay, that's what it means. Objective is soft probability. And then soft, it's also called when you have multinomial class, this is what we use. Okay, and this is the evaluation matrix, is the m log loss, that is the close to the entropy. Remember that number of class is num class. Okay, so you set all these parameters first, and then you run it. You train the model. Are you with me so far?
Sir, ETA is what, sir? ETA?
That is the stopping rule.
ETA is what, sir? Sorry.
That means when it reaches the 0.001, the error stop. Okay.
When it reaches 0.001, sorry, sir.
When the loss reduction reaches 0.001, then just stop.
Okay.
You need a stopping rule, right?
Yes,
Yeah,
sir.
that is the stopping rule. You can also do a stopping rule with the number of trees. This is one way. Okay. Are you with me so far?
Yes, sir.
Yes, sir.
So if it will keep on doing the trees, but it doesn't have to reach all the way to the end of the trees, like 10,000 in this case, for example. If it reaches 0.001, we just stop. That's a stop. And then we want verbose means we want a detailed output. No, 0 means no detailed output. So let's run this and then print the fit. This is what the fit will look like. Okay. The fit values, the objects, it has many of the objects, it will print all those things. Okay, one second, let's run and see what happens. It is running right now. It is using number of threads is only one, it's not really doing a parallel processing. You can use, I have 8 threads in this one, I can use 2 or 3 or 4. See, because it's a number of features is 4, we take 4 because of this value. Okay, column sampled by tree. Column refers to variables, subsample refers to rows. Okay, 75% every time it takes. So this is the output. We can predict that now for new data, for the test data we can predict it. That's what it is here. xgb.fit is your object model object, test data, and then reshape is transposed. Okay, xgb predict is as data frame it is created. xgb predict is now recast into data frame. Column names are basically levels. Okay, column names are basically levels. So it's going to give probability, predicted probabilities, 3 probabilities. That's what this means. Do you agree? I think that's what it should be. Let's see. Column names. Column names are just the levels. So let's see. Let's predict the identify the class with the highest probability. So wherever it is highest probability, we are going to put it as the predicted class. Is everybody good on that one? Because there are 3 classes, right? Yes.
Yes, sir. Yes, sir.
Okay. So it is now I have predicted also predicted values. So predicted labels are here. Add xgb.pred $label. It's a predicted labels. Do you understand what I'm saying? On the other hand, xgb predicted fit xgb. One second. This is the fit. XGB train. Let's see XGB train. Levels. Okay. I'm not sure it will come. Let's see. Because it is a separate data set. LS, let's see. XGB. That is. So it's a different data set. We can't just get it like that. So the predicted labels are fine. We got predicted labels. The prediction also we can get. Let's go and check it out. XGB pred. Okay, these are the predicted values. Everybody, predicted label is this. These are the predicted probability values. Everybody gets it? So because it is the maximum is here, you got setosa as the prediction class. Label is also assigned to setosa. Okay, so if you look at the this, you can view xgb.pred. As for this, so you can see that here for all the data here. So here this is the maximum here. So that's why it's labeled as versicolor. Okay. In this case, this is the maximum here. So I'm sorry, but this is the maximum, but somehow it is identified as versicolor. So prediction is saying this label is not correct. Label problems are there. I don't know why. Prediction is correct, Virginica. Okay, label problem is there. Label is based on. Label is based on. Let me check. Label is based on levels of species test dot label plus 1. That's what predictor label is. But prediction is correct. Are you with me? Prediction is correct as Virginica, but versicolor is no label. Labeling is there. There's some problem with the labeling. Try to be careful. This formula is not really working well for me. Okay. I just see that. So let's do now how much accuracy is attained. How much accuracy is attained? Label, predicted label divided by n row predicted. Okay, so that's what it is. So I'm going to do that predicted label, but we'll come back and check it out with the prediction.
Sir.
Yes.
So that I'm not able to interpret that table, sir.
This
prediction label, sir. There are values for
the prediction is coming from the system. Label we give you a label. Okay.
Sorry, sir.
Prediction is coming from the system, but label we gave. Labeling, there was a problem with the label. I don't know why. First of all, it gives a label. You can use just the prediction. So that's what I'm going to do right now. We did according to this. Their notes. It turns out to be. 1 second. I'm going to use only the prediction. That's my point. Are you with me? Okay. So 1 moment, please. No, we don't want to do it. So I want to use, let me use the prediction. Okay. Not the label, I want to use the prediction. Something is not. Okay, it's keep trying to write. Okay. I'm going to do this. But this time I'm going to say prediction. Okay. %, correctly predicted. So I'm not sure why they would. It is based on prediction. Oh, okay. This is the way, the other way. These are the actual label, but this is the predicted values. Okay, now you understand what I'm saying? These are the actual labels, but this is the predicted labels. Are you with me? It makes sense now. I see. Are you with me?
Yes, sir.
So we take the labels. If it is, prediction is equal to label, that's the one we call it as, if it is equal to this, this is the logical equal, right? So it becomes 1, otherwise 0. So it is the sum of such equalities and then divided by the number of rows. Okay, the number of rows in the XGB pred. The XGB pred size. Let's see the XGB pred should be 112, I think, right? Dimension XGB pred. No, this is the test data. Okay, out of 38 sample, okay, 92% are predicted correctly. Are you with me? Everybody?
Yes, sir.
This is fine. This is the actual label. This is the predicted label. Is everybody's good?
Yes, sir. Yes, sir.
Okay, now I want to give one more example. Let's go to this one. Adaboost. So right now I did the XG boost. Shall we do the Adaboost for the same data, iris data?
Yes, sir.
Okay, good. And we'll review this one more time to next class also. So here is, but this is predicted. Look at this one, confusion matrix. This is predicted for 150 observation, not for the test data alone. See there, I did it for test data alone, right? We can do the test data, training data here also, but let me review this for you. This is a reference I will give you. You have to go through that reference. Here is the reference for you. Okay. Copy. It's a big. Control K. I got it from bring it from there. Control A C. This is the one I'm talking about. Okay. It's a big, big link. Just copy it and keep it with yourself. Okay. So in this one, let's go there. It's open. It's open. It should not open again. Same thing, right? Okay. So in this case, let's review that for you. In this case, it's an Adaboost this time, right? So here I have the data iris. Train is 1 to 50, 50. I took everything as training. Are you with me so far? And then we are doing the boosting species as a function of all the available variable. And then take the data is iris train. 10, we are building only 10 trees. Maximum depth is 1. Okay, don't go more than one depth, because it's always left and right, right? And for any variable, it takes left and right, and we don't want more than one split. That's what Adaboost is all about so far. That's what we know. Okay, and that's what we have been using it. So, so we kind of and then so we built the model. It automatically takes 75% of them as sample to build, and 70% is tested, I think. Okay, because it says only n is 75. It is using only 75. Now, wait. Number of trees 1. Number of trees is 75. Is that correct? Formalized basis is this one. N is 75. Split n loss y value denotes terminal node. Okay, so it's going to print these things. Root is 75, 46. N is 75. Okay, N is, it does take 50% observation, right, for the training, and it is building every time N is 75. Okay, everybody so far so good? Yes?
Yes.
Okay, I have to see you. I don't want you to feel that I'm rushing right now. I'm not. I want to give you this, complete this one. Is everybody with me? It is building automatically 75 observations as training. And then you build so many of these trees, and then predict that using all those trees, 10, I think it is depth is 10 trees, right? So here is it. 10th tree is the last one. Are you with me? Trees within parentheses, square parenthesis is 10. That's the last tree. And then we use the voting method. What voting is used to predict, and these are the predicted probabilities. So accordingly, the first observation will be categorized as setosa. Everybody, second is also setosa. Up to the 25th is also setosa, but not the 26th. 26th is versicolor. Okay, like that. Everybody.
Yes, sir.
And then here is the bar plots, Adaboost, variable importance. In the variable importance, petal length is the most important, and then petal width, nothing else matters in the modeling. Okay, and then the confusion matrix turns out to be like this. The error is 5.3%. Are you with me, folks? There it was, how much was that? It was, I think, the previous one in the XGBoost, I have the error to be 8%. You remember? But it's a different, the test is separately, set aside 38%, I mean 38 observation only. Are you with me? But here it is different. Are you with me so far? Okay.
Yes.
Okay. I'm not. I don't want to. I don't want to rush, but this is what it is. So we are taking Adaboost model, predicted class, observed class. We are doing that. This is the predicted class, this is the observed class, and some Adaboost class versus iris species training. Okay. This is only done for the training. That's why it is less. I want to tell you why it is. Error is less. Are you with me?
Yes.
It's a cheeky, I kind of passing all these things. It may look like I'm kind of passing this off on. It looks like Adaboost is better. No, we are only testing it for first 70 observation training. That is, you will have to do this for test the remaining 70 observation. Okay. So far so good, everybody. Now we are talking about prediction for minus train. That means testing data. Are you good, everybody? And these are predicted probabilities. These are the predicted classes. Now it so happens for testing also only the same turned out to be 3 errors on this side, which is 4% error. It can happen. So we can also do cross validation. Boosting.cv runs v4 class cross validation. So here it is, boosting.cv function. You can use it for Adaboosting as well as for XG boosting. So far so good, everybody? Always use cross validation. Please write it down. Always use cross validation. CV. Always. It's very, very important. Okay? Everybody is good?
Yes, sir.
Okay. So cross validation is what? You are splitting it into multiple samples, isn't it? Not just what training and testing, but multiple samples. 5-fold means 5 splits, 10-fold means 10 splits. Usually 5 or 10 is okay. 5 is good enough also. Okay. So that is what is done. When we do the cross validation, actually there is more error. That means it was over predicting in the previous case. But it says 4.6%. Oh, in the cross validation, you use all the sample. You see this one, the whole data set is used. There is no training and testing because you are splitting into 5 parts. Yes? Everybody gets it? Yes. Gauri Shankar, Vinesh, Gautam, Ramkumar, Jeffrey.
Yes, sir. Yes, sir.
Jeffrey?
Yes, sir.
Okay. Arun, are you there? I don't know. Okay. Jeffrey?
Yes, sir.
Okay, cool. So in cross validation, you're using all the data set. That's a very important point, right? And it turns out to be, because it is 150 observation, even though here it seems 7, it's really 4.6%. This is more reliable. Is everybody good with me? Okay.
Yes, sir.
So that is what I want to share with you. So I have compared 2 right now, the XGBoost and XGBoost also has cross validation. XGBoost and the Adaboost. We can do for randomforest also. I want to stop here. Any questions? I'll finish. Maybe bagging is really the randomforest. Iris bagging important per product. Train, but because of the train, it's giving there's also a method called bagging, okay? That is bootstrapped aggregation method, bootstrapped aggregation method bagging. So that comes out to be 0.46. Let me finish that statement before I hear your problem. 3.67% error, 3.7% error. Let me complete this. We will review this again. Don't worry about it. Bagging related CV 10-fold cross validation applied with bagging which is basically the the so now when you use the tenfold, you get a 12.6% error. Are you with me so far, guys? Okay, everybody with me?
Yes, sir.
Okay, excellent. So my point is that I have compared all these things. We will review this one more time because there are a lot of little interesting things I have pointed out. Go ahead. What's the question? Somebody said raised voice. No?
Sir, XGBoost, where's the error percentage? Sir, we didn't see it right. I want to see the error percentage. Where we saw the XGBoost. What was the error percentage?
Sorry, XGBoost was 4% with the test data set. You remember XGBoost was adabag. XGBoost is here, not this one. Once again, XGBoost. It's a different. R later. I thought, yeah, okay, fine. So XGBoost has 8% error, but it's set aside one test data set. There are still some variations in between, so it's not 100% apples to apple comparison, okay? But because that I didn't do XGBoost CV, I should do XGBoost CV. But you see, the CV is always higher, right? It will be higher because you are considering more variations on the test side. So it will be higher, and it should come down to less. I believe it will come down to less because we don't know. It may be a randomness issue here. The 30 sample that turned out to be whatever it is probably contributing to this. So if you want to compare all of them should be CV based. Is everybody's good?
Yes.
Okay. Supriya, this is a great example to go through as a lab also one more time with them. Okay? All right.
Will do so.
All right. Any other question?
No, sir.
So we have come round a full circle on boosting methods, random forest, cross-validation methods, and so on. Okay. So we will, in the lab class we will review this particular iris data set. We will review that because it's a small data set. You can quickly do, but there are a lot of little things you want to, take it in. Okay. In your thinking.
Sir, while running the R code and getting errors, sir, the num class should be greater than one parameter must be set for multi-class classification.
Right. Why is that? I ran that one, right? Num class, I ran.
Actually, everybody is getting except me.
Maybe num class you didn't define it before. See, there was a definition of num class. It is equal to num class is equal to number of species, right?
Length of level of species.
Number of species, yes.
Yes, sir. I have done that also, but I'm still getting error.
I'm not sure why you would get num class equal to num class. One moment. It should be 3. Let's see. See, num class is 3. You see this one?
Yes, sir.
Yeah, it is set as 3 in our, in my notes. It is set as 3. That's why you have to. There is a command there that you have probably missed it. In the way it should be done. Let me see. I gave you the reference, right? Can you go back and check it out? It is not in
Yes, sir. Probably value is showing as 0n, sir.
So it's not correct. Yeah, that's the problem. Yeah, it's a num. So num class should be defined as an integer class.
So PL.
So if you, I think there is rpubs maybe num class. Okay, here is. 1 second, huh? I remember it was defined somewhere. Okay, so here it is. I think. Let me see. Okay.
Define the main parameters, sir.
See, length, levels, species. இது மாதிரி தான் போட்டீங்களா நீங்க? இது போட்டீங்களா?
அதுதான் சார் copy paste பண்ணிருக்கேன்.
But the thing is, no, maybe species was defined. You have to define the species correctly. You know, see here it is. Species equal to iris dollar species. Is that what you did?
அதேதான் சார், everything copy paste தான் சார்.
Uppercase number. I think you didn't define. You probably you did not. It didn't work in your case or something like that. Okay. Just use this one. I thought I gave this list. Okay, let me give you this reference also one more time.
Okay. அதே same markup தான் யூஸ் பண்றேன். marking வந்து same தான். இங்க when I'm checking num class it is showing as 0L.
Yeah, it cannot be 0L. So that means this didn't work or this didn't work. One of those two. Only two places. This going into class. This one.
Sir, he always gets a different answer. It's not the first time. Every time I take a practical session, he always gets a different output. Always. I don't know how.
Okay. All right. You know, you go through this very carefully. You'll be fine, Gautam. Okay.
Okay, sir.
Okay, no problem. Thank you, everybody.
Thank you, sir.
Thank you, sir.
Be cheerful until I see you next time. You have 7 days. Don't get down. Okay. You're going to be happier, cheerful. You are learning. It's a big deal. You know,
Sir, one more.
your brain is active. You know, you are creative. Come on, you're eating, you're sleeping. Why you should be smiling always. Okay? Yes.
Yes, sir.
Abba, rendu பேர் தான் மூணு பேர் தான் சொன்னீங்க. Yes,
Sir,
Gautam.
class please.
Yes, Gautam. Arun.
Yes, sir.
Yes, double up, double thumbs up. Gautam, Ram. Okay, only single. You know, okay, he's not sure. Gauri Shankar. We'll see next Sunday, Saturday.
Sir, you have all the clustering video, sir.
I'm going to post it. I'm going to post it today.
Okay, sir.
Two videos. Okay.